Today, we're going to talk about one of the most fundamental rules of the entire cosmos. It's this single, elegant idea that explains the incredible dance of planets, stars, and whole galaxies. This is the invisible force that literally shapes worlds. And it all kicks off with one simple question.
Really think about that for a second. The Earth is constantly pulling on the moon with this immense gravitational force. So why isn't it just falling? Why doesn't it come crashing down? Well, the answer is one of the most beautiful and profound discoveries in all of science, and we're going to figure it out together, piece by piece. You see, the secret isn't some special rule just for the moon. It's a concept that is truly universal. The exact same force that makes an apple drop from a tree is the very same force that choreographs the massive orbits of planets. It's like finding the one rulebook that governs the entire cosmos.
And here's the rule, put into words by the one and only Sir Isaac Newton. The most important word on this slide, it's every. You, me, the planet we're on, the most distant star you can imagine, if it has mass, it's part of this cosmic web constantly pulling on everything else.
So how strong is this pull? Well, it all boils down to just two things. First, mass. The more stuff an object is made of, the stronger its pull. That's why a giant like Jupiter has way more gravitational pull than Earth. And second, distance. The farther away things get, the weaker that pull becomes. It's this beautiful, simple dance between mass and distance that plays out across the entire universe. Now here's where things get really cool. Newton didn't just give us the idea, he gave us the actual math. He came up with a formula that lets us calculate this force with incredible accuracy. And there it is. I know, equations can look a little intimidating, but don't worry, every single part of this tells a piece of the story, and we're going to break it down right now. So let's meet the cast of characters here. F is what we're solving for, the force of gravity. M1 and M2 are just the masses of our two objects, say the Earth and the Moon. R is the distance between their centers. And that big G? Well, that's kind of the secret ingredient that makes the whole recipe work.
This little number is G, the gravitational constant. And just look at how incredibly, ridiculously tiny it is. That's a decimal point followed by 10 zeros before you even get to a number. This is why you don't feel the gravitational pull of the person sitting next to you. The force is absolutely there, but G is so small that you need something with the colossal mass of a planet for that pull to become noticeable at all.
Okay, so let's bring this giant cosmic law all the way back home, because this universal force is responsible for something we all experience every single second of our lives, our own weight. Now, people mix these two up all the time, but in physics, they are totally different. Your mass, that's just the amount of stuff you're made of. It's the same whether you're on Earth, the moon, or just floating in deep space. But your weight, that's just the measurement of gravity's pull on your stuff. And because of that, it can change depending on where you are. So that leads to a pretty cool question, right? If your weight is just gravity's pull, does that mean you weigh the exact same amount everywhere on Earth? And the answer, believe it or not, is no. The Earth isn't a perfect sphere. It actually bulges out a little bit at the equator. This means that if you're standing at the equator, you're technically a tiny bit farther from the Earth's center than if you were at the North Pole. It's a super small difference, but it means you actually weigh fractionally less at the equator. How wild is that? All right, we have all the pieces of the puzzle now. We understand mass, we get distance, and we know about the force of gravity. It is time to go all the way back to our first question and finally solve the mystery of the moon. So there are two crucial things happening at the exact same time, locked in this perfect celestial dance. First, the moon has inertia. It wants to keep moving in a perfect straight line. If you could just poof the Earth out of existence, the moon would just shoot off into space forever. But at the same time, you've got Earth's gravity constantly yanking it inward, pulling it toward us. And the result of that cosmic tug of war is a stable orbit. You see, the moon is in a constant state of falling toward the Earth, but its forward motion, its sideways speed, is so perfectly fast that it constantly misses us, curving around our planet instead. So it's not that gravity isn't pulling it down. It is. It's that its speed perfectly counters the fall. And this brings us right back to the beginning. The simple force that pulls an apple to the ground is the exact same force that bends the moon's path through space. It's one single, universal, and absolutely beautiful law. So what are the big takeaways from all this? First, gravity is everywhere, connecting everything with mass. Second, its strength just comes down to mass and distance. Third, Your weight isn't some fixed number, it's just gravity's personal pull on you. And finally, those amazing orbits we see in the night sky are just this perfect balance between moving forward and falling down.
So I'll leave you with one last thing to think about. If every single object is pulling on every other object, what invisible strings are the distant stars tugging on right now? What forces are playing out across those unimaginable distances this very second? It's something to ponder. Thanks for tuning in.